today to speak to us. And I would also like to mention that all the attendees should keep their mics in mute. And if you have a question at the end of the session, you can type it in the chat box, and we can I will read them out to you. Professor Shastri.
Thank you very much. Thank you very much for this opportunity. It's always a pleasure to talk about my work and related topics to an audience of science buffs. So, so the hunt for the heftiest things we know was my title, and I think all of you know that the heftiest things we know are indeed black holes. So I will try to tell some strands of the story of black hole discovery. So to start with, what are black holes? Black holes are chunks of space-time from which even light cannot escape, right? So space-time sounds fancy, but it's just a fancy way of giving the correct description of where one is. So, for example, if I say I'm here in my home, that's not a complete description, because I should say I'm here in my home now, because I wasn't here last week and I may not be here tomorrow, right? So that's what is space-time, here and now is my complete description. So that's an intuitive way of thinking about what space-time is. So black holes are chunks of space-time from which even light cannot escape. So I said escape. So can we use the concept of escape velocity to try and understand black holes? So you will recall from your high school physics that there is this relationship between the mass of something and how far one is from the center of that thing and the speed one needs in order to escape from that thing, from the gravitational field of that thing. And we call that escape velocity. So for example, from the Earth, if I jump, I'm going to fall back in unless I launch myself at a speed that is larger than or much larger than about 11 kilometers a second. So that's what we call escape velocity, right? Now, suppose you keep the same mass, but compress it to a smaller size. So for example, if we squeeze the Earth to a smaller size, then the escape velocity at the surface of that body, the Earth in this example, would increase. So the escape velocity at the surface would increase because the distance from the center would increase, this number r. So I wanted to ask, can you see my cursor, Vitasta?
Yeah, I can see the cursor.
You can see my arrow pointing at the letter R?
Yes.
Okay, that's great. Okay, so as I said, if you squeezed a mass to a smaller size, then the escape velocity from its surface will increase. Now, what if you just kept on squeezing it and increasing the velocity to a very large number? In particular, suppose in this formula, you set the velocity to the velocity of light, which is 300,000 kilometers per second. Then in the formula, you will get this relationship, which is really a relationship between the mass and the distance from the center, which is effectively the size. So rewriting that, you get this relationship again between the r, which is the radius of the object we're looking at, and its mass. And it's saying that if a given mass m is of this size, then the escape velocity will be the velocity of light. In other words, even light cannot escape. And that is what people call a black hole, right? Because that's what I said to start with, a chunk of space-time from which light does not escape. Now, this idea is actually a very old one. There is a documentation of a parson called John Mitchell, who was also a scholar in Cambridge University, who talked about this in 1783. and talked about very massive objects and the escape velocity being extremely large and therefore us not being able to see them. That's a sort of very intuitive idea of what black holes are. But it turns out it's not the complete picture, because there are consequences of mass, some consequences of mass, which are not quite intuitive, which is another way of saying that it's not quite, it doesn't quite follow the physics that was known before Einstein. So all of you have probably heard of one of the very famous discoveries of Einstein, which is general relativity. The same year that Einstein proposed the theory of general relativity, Carl Schwarzschild predicted black holes using this theory. A more fancy way of saying that is that he found a solution to the equations of general relativity. And it turned out that the relationship between the size and the mass of an object implied by the theory was exactly the same formula that I pointed out earlier. Using just the concept of escape velocity. Now that's quite fascinating, right? Because the earlier we got the formula from very simple classical concepts, and now I'm saying that general relativity also gives the same formula. So that is fascinating in itself. But there are certain consequences of masses which only general theory predicts and which the classical theory before that did not predict. In particular, general theory of relativity predicts that masses will bend light. And this was a very interesting prediction, which then Arthur Eddington confirmed in a famous experiment around the 1919 solar eclipse, where he found that the mass of the sun can bend light, measurably so. They actually measured that bending, and it turned out to be exactly what general theory of relativity predicted. Now we think of, we know that light travels in what are known as geodesics. And what are geodesics? They are just the shortest path between 2 points. Sorry?
May we request everyone to keep their mics muted?
Then 1401 and 1508. So 1401 will become 1.
Vitasna, maybe you can mute his mic.
I muted it.
No, I can still hear. Okay.
Yeah.
Yeah. So when there is a mass, it bends light, is what I just said. Now we know that light travels along the geodesics, which is the shortest path between 2 points. And we think of the shortest path between 2 points as straight line. But if a mass is going to bend light, that means that the shortest path between 2 points is not a straight line, but is curved. In other words, the space-time itself should be curved. So this is a non-intuitive consequence of the general theory of relativity, and it is very nicely summed up by John Wheeler, who said, mass tells space-time how to curve. Obviously, any mass does this. So my mass, your mass, my laptop's mass, all of them curve space-time, but the amount of curvature is exceedingly small, and so we never notice it. And we think everyday space-time around us is actually flat. So it requires a rather large mass to to give rise to a measurable bending or measurable curvature, and that's what Arthur Eddington measured using the solar eclipse. And so you can imagine that for a black hole, where it is a very, very compact object which has to satisfy this relationship, for the kind of curvature, so this grid represents sort of a flat space-time. If you would put a black hole in there, you would get an extremely large curvature of the space-time. So if it's a very small mass, the curvature would be almost imperceptible, and as you keep increasing the mass there without, let's say, increasing its size, then you will get very little curvature at large distances from where the mass is, and a very strong curvature where the mass is. So that is what I meant by the non-intuitive consequence of mass, of a mass being in space-time as predicted by general theory of relativity. And as you know, this is not something really obscure. This is something we use in our everyday lives, because even the mass of the Earth is large enough to curve space-time around it, so that the GPS system that we use on an everyday basis has to take into account Einstein's theory of general relativity in order to function properly. Okay, so to go back to this formula, the question is there a minimum mass for a black hole? Are there electron-sized black holes, or are there black holes seen in the laboratory? And the answer is that in the laboratory, there has been no evidence so far for any black holes. There has been speculation about micro black holes, the size of an electron, and so on. There's this whole very interesting Wikipedia page on that. But the only real black holes we know are in the cosmos. So, in fact, as early as 1939, Oppenheimer and his collaborators predicted that stars at the end of their lives could collapse into black holes. And so the question is, have we seen them? How can we see them? It's not that easy, right? Because black holes, by definition, are black. There's no light coming from them. So then how do we see them? I wanted to mention a result that was discovered by C.V. Vishweshwara, Vishu as we knew him, who was an astrophysicist who lived in Bangalore for many, many years in the Raman Institute, and then in the Indian Institute of Astrophysics, and he was the founder director of the Bangalore Planetarium and so on. He had found in 1970 that the black holes were stable. In other words, he looked at the Einstein solution of the so-called Schwarzschild metric, which defines a black hole, and he showed that the object. Hello.
Yeah, it's fine. Please carry on.
Okay, there's no echo, right?
There's little bit echo.
I wonder why that it suddenly started.
Yeah.
Okay, if it's not too disruptive, I'll continue.
Yeah, it's okay. It's fine. Continue.
Yeah. So Vishu discovered that black holes were stable, and that is really critical to being able to observe them, because if they are not stable, then they would just form and disappear, and there would be no chance of actually seeing them. So before going further about how we can see black holes and search for them and so on, I wanted to indulge in some digressions to get over with some definitions and some techniques that astrophysicists use in order to understand what happens in the sky. So first of all, the unit of luminosity or power, we tend to use one solar luminosity as the unit of power. So one solar luminosity is roughly 3.8 into 10 to the 26 watts, which is of course a lot of power in the usual units. It's a big number in the usual units. So we use solar luminosity as the unit. So we might say such and such is half an L sun. That is what this symbol is, L sun, or 10 L suns or whatever. Similarly, the unit of mass, we use the mass of the sun, which is about 2 × 10⁻30 kilograms, and we use that as a unit of mass in astrophysics. So something is 10 m sun, for example, which means it's 10 times what the sun weighs. So the workhorses of astrophysics are obviously telescopes, which focus the light onto a detector at a whole variety of frequencies. So here is the dome of the Venu-Bapu telescope in Kavlur, which is operated by the Indian Institute of Astrophysics, and the telescope is in there. For many years, it was the largest visible light telescope in the country. Now the largest is in Uttarakhand. This is the giant meter wave radio telescope outside of Pune, operated by the Tata Institute of Fundamental Research. This is the famous Hubble Space Telescope. This is the Chandra X-ray Observatory. And this is AstroSat, the Indian astronomy satellite that is up right now and operational. So those are just a few examples. So these telescopes operate at a variety of wavelengths, and they have sensors in them which capture the photons that come from the cosmos. And so the technique of detection changes depending on what the frequency is. So for visible light, it's very similar to the cameras that are in our CCDs, similarly with with the Hubble Space Telescope. But when it comes to radio frequencies or X-ray frequencies and so on, the technology has to be different because the physics is different. One very important piece of technology that astrophysicists use is spectroscopes to do spectrography. So spectroscopy is very, very important for a variety of reasons. So what spectroscopy does is it splits the light into the component frequencies with varying degrees of sharpness. So as you know, if you look at the sun and a rainbow, the rainbow is a split up sunlight, which is done by little droplets of water, which act as prisms. Now, a spectrograph spreads the light to a much larger degree so that you can see the so-called spectral lines, which occur because of atomic transitions. So here is an example of a spectrum. And so you can get, okay, let me look at this first. So here is an example on the top of a spectrum, and you see a rainbow-like spectrum, and you see dark lines. Now these dark lines represent the spectrum of a gas that is in between the source of light and us. So that's when you see absorption lines. This spectrum, on the other hand, represents an emission line spectrum where you see spectral lines from this gas, but the gas itself is emitting the photons. And so the atoms in excited states are emitting lines, and you see the spectra. Now, one might think that spectroscopy tells us about the composition of the kind of things we're looking at, which is true. But in an astrophysics context, it's way beyond that because of a couple of different reasons. So first of all, yes, it tells us about the composition, provided we are able to identify which spectral lines these are. That is, which atomic species is giving rise to these spectral lines. But on the other hand, there's also the shift in frequency of the spectral lines because of movement of the source of light. And so if a star, for example, is moving in a line of sight away from us, the spectral lines will be shifted to shorter frequency, lower frequencies. And if it is, if it's moving away from us, it will be shifted to lower frequencies. And if it is coming towards us, it will be shifted to higher frequencies. So if we can unambiguously identify which spectral lines are appearing in our data using laboratory measurements, then we can determine the speed at which this star is moving in our line of sight and whether it's moving towards us or away from us. So this is a very, very powerful technique that astrophysicists use. They can use spectroscopy to determine the kinematics of whatever they're looking at. There is another thing, which is looking at the spectrum as a whole. That is, what are the different elements that have been excited and what are the excitation lines that we are getting? That, of course, directly relates to the temperature of the gas that is emitting these spectral lines. So spectroscopy also gives us a handle on the temperature of the source that we're looking at. Furthermore, there is something called a cosmological redshift, which is, we all know that the universe is expanding, and because the universe is expanding, everything that is every sort of system that is gravitationally bound is moving away from another system, and therefore, sitting here on Earth, if an object is sufficiently far away that I'm beyond the point where I'm just looking at the kind of circular motion or random motion or something that that object is doing, then I can actually see a shift in the frequency of things emitted by that object, and that shift gives me a handle on the cosmological redshift and therefore on the distance. Because as the universe is expanding, the further an object is, the larger will be the stretching of space between us and the object, and therefore the larger will be the shift in frequency of things that the object emits. So therefore, by measuring cosmological redshift, I'm able to measure how far objects are from us. Another very powerful technique is comes from this idea of Keplerian orbits, which we already alluded to earlier. So things that are in gravitationally driven, for example, like the Earth, like the moon is driven gravitationally by the Earth, and then the Earth is driven gravitationally by the sun into an elliptical orbit. And if that is the case, then there is a relationship between the mass and the distance and the speed. So if one can measure any two of these parameters, one can then infer the third. So this is another very powerful technique that astrophysicists use. Another powerful technique is something called the light travel time argument. So I won't directly be using this in my talk today, most likely, but I just wanted to describe it to you because it's a very powerful argument. So imagine that you have an object here, very far away in the cosmos, and it's after some time, I mean, you're observing it continuously, and after some time, it suddenly brightens, let's say. Now, this object is quite far, and therefore light takes a finite amount of time to reach from the object to our telescope. And the photons have to come to us from all parts of this object. So both photons from the front, photons from the back, photons from the middle. So this represents a photon from here, and this has to travel this distance. And this represents a photon from the backside of the object, as seen by us, which has to travel this distance. So you can see that there is a delay between the photon that came from the front to the photon that came from the back. I'm sorry. So as a result, if you keep on watching this object, although the object instantaneously brightened, let's say, from this state to this state, we will not see an instantaneous brightening of the object. We will see the brightening spread over some amount of time, and that time will depend on the delay between the first photon and, or rather the photons from the front part and the photons from the back part. And so that is exactly related to the size in our line of sight. So in other words, even without having sharp enough images to see how big this thing is, just by looking at how much light is coming from it and monitoring that with time, if we see changes with time, then we can infer the size a limit on the size of that object. So this is called the light travel time argument, and it is also a very powerful technique because it's not that easy to get, very sharp images of things very far away. So this is just an example of what that kind of data set might look like. I mean, this looks very boring, but what is plotted here is the intensity at different frequencies in the different panels as a function of time on the x-axis. And you can see that the points are going up and down, up and down. Some of these fluctuations are just random fluctuations, but some of them, like you can see here, there's a systematic change in the amount of light we see. And the time scale on which this has changed, for example, this many days in this case, that gives us a handle on the size of the thing that is emitting that light. So that's the light travel time argument. Another thing that I need to point out is that in astrophysics, we are always out of date, right? You know that. Because, for example, from the moon, light takes 1.3 seconds to reach the Earth. So whatever we are seeing about the moon happened 1.3 seconds ago. From the sun, it is 8 minutes ago. And then when you go to further away to stars and galaxies and so on, it's that much further away. Now, you might think this is a disadvantage, but actually, in some sense, it's an advantage because if we want to know what happened in the past, if we want to know the history of some chunk of the universe, all we need to do is to look far away. Because astrophysicists understand this idea that of the cosmological principle, which means that the universe is sort of uniform everywhere, not on the scale of a solar system or a galaxy, but if you take a very large chunk of space-time, it's roughly uniform. So if we want to know what happened here, in here as in, let's say, in the Milky Way, what we need to do is look further away, because there would be another roughly Milky Way-like thing over there, and if we look at it far away enough, then we will see how it was that many billions of years behind. One more point about data visualization. So this is the electromagnetic spectrum, which you're all familiar with. And I just wanted to talk about the idea of false color pictures, because in astrophysics, we take images at all frequencies, right from radio through infrared, visible light, etc., X-rays and gamma rays. And it's only the visible light is a very small chunk of that. And if you look at this picture, the picture of a cat, that's how we would normally see a cat. If I took an infrared picture of that cat, how would I render it? So one way to render it is to use colors to indicate intensity. So that is what these two pictures are. So in this picture, as we know, a cat's eyes are warm, and so it will emit more infrared light, and the nose is cold, it will emit less infrared light, and the body will emit something in between. And so this rendering has used the yellow color to represent, white to represent the maximum infrared intensity, and black to represent the least, and some other colors in between to represent intermediate intensity. So here, color is not real. That's why it's called a false color picture. And a false color picture simply represents the intensity of the light at that frequency and has to be interpreted along with a key like this. And so this and this are the same data. It's just that different false colors have been used in this case to represent the same data. So if you look at an astronomical picture, so for example, these two galaxies, these are what are called true color pictures. So they are very close to what the eye would see if the eye could see such sharp images. In other words, you take the red, the green, and the blue light and mix them in such a way which is very similar to what the eye would see. Here, on the other hand, are false color pictures. So here is a famous sombrero galaxy. This is how it would look in sort of visible light. And this is a true color picture, but these are false color pictures. So this is how this galaxy looks in X-ray light. This is visible light. and this is infrared light, and here it's all superposed one over the other, and all of these three are false color pictures. So false color pictures are a nice way to render images which are obtained in frequencies other than visible light. So that was just a digression. Okay, so back to black holes. Now, as I said, the only black holes we know are cosmic, and even John Mitchell back in 1783 had realized this. And in fact, when he talked about objects with a very large escape velocity close to the velocity of light, he talked about dark stars. So he already was talking about, because the only massive objects had to be out there in the cosmos. So in order to, the story, of course, starts, you can say, with John Mitchell and Laplace and so on, but just to give you some strands of it, Meghnad Shah applied quantum physics to the ionization of stars, and that gave a relationship between the temperature and the spectra that we see of these stars, which was very key to interpreting the spectra that were obtained from stars. So as you know, we see the Fraunhofer lines in the sun, and if you, for example, if you point a CD at the right angle, the grooves on the CD can act like a diffraction grating and spread the light, and you can actually see these Fraunhofer lines. Now, every star has lines like that, and I showed pictures of that earlier as well. And so the lines that we see not only tell us about the composition, but they also tell us about the temperature. Now, before this work, it was sort of thought and assumed that the composition of the sun and the composition of stars was the same as what we see on Earth in terms of all the heavy elements and so on and so forth. But when Meghnad Shah came up with this relationship, an astrophysicist by the name Cecilia Payne-Gaposchkin applied the theory of Meghnad Shah to the spectra that she had of a bunch of stars, and she concluded that this was not correct and that stars were mostly hydrogen and helium. So she concluded that the composition of stars was very different from the composition of the general of stuff that we see around on Earth. It's very interesting because when she did this on her own, and when she came to this conclusion, her supervisor, who was a very renowned astrophysicist, didn't believe her results. And so she, in her thesis, she had to include a sentence to the effect that I think these results are spurious, just to satisfy the supervisor. I mean, needless to say, one needn't discuss what happened to her morale, but it was actually a really fantastic discovery, and today it is seen as worthy of the Nobel Prize. But in fact, the Nobel Prize, this result did not get the Nobel Prize, but her supervisor, who did not believe her results, actually got nominated for the Nobel Prize based on this result, which is quite interesting. Of course, the positive side is that her supervisor, after a while, did independently check what she had done and then agreed with it, and then corrected the previous impressions. So then there was the whole question of what happens to stars, which are mostly made of hydrogen and helium. And without going into a whole lot of detail, Oppenheimer and his collaborators came up with the idea that at the end of their lives, stars could collapse into very compact objects, including black holes. So one step before the black hole is a thing called magnetized neutron stars. And these are also extremely compact objects. These are also objects which show curvature of the space-time and effects of general relativity. And they were discovered by somebody called Jocelyn Bell. It was a very painstaking discovery. It was using a radio telescope, which she built herself, and it was at a very low frequency. So these were a bunch of sort of aerials in England, a lot of digging and installing involved. And then there were these pen charts, which recorded the radio signal that came from them. And there were these reams and reams of pen charts, which she interpreted, which she analyzed while looking at the sky. And she saw these pulsing stars in the radio, and these were the magnetized neutron stars. Of course, this is another story where it was her supervisor who got the Nobel Prize for this landmark discovery. So now, how does one hunt for these black holes which arise as the remnants of stellar death? So one possibility is if a black hole is together with another star, gravitationally bound. And remember, I talked about Keplerian orbits. So if one can see the other star and measure its speed and how far it is from the other gravitating body, then we could infer a mass and we could check whether it satisfies the black hole relationship. So this method, I will not go into the details of this method because that is not the focus of my talk. But with this method, about 66 black holes are known, and 66 black holes whose masses actually have been estimated. And in the whole Milky Way, it is estimated there are about 10 million such black holes that are scattered everywhere, which are the result of the stellar evolution and stars dying and leaving behind a black hole. So the smallest black holes are of a few solar masses. Remember, I said that the solar mass was the unit of mass in astrophysics, so a few solar masses. And then recently came LIGO, the Gravitational Wave Observatory, which measures gravitational waves, which are ripples in space-time. And two very compact objects, whether they are magnetized neutron stars or black holes, if they come together and get attracted and then spiral in and collapse, they will create ripples in space-time, and that's another way of hunting for black holes. So such a merger or coalescence of two black holes was actually detected when LIGO went online, and this is the iconic result. I will not go into the details, but I would recommend that you listen to the announcement, the LIGO discovery announcement, the very first time, where the spokesperson Gabriela Gonzalez gave a very evocative description of that discovery. So now I want to come back to our Milky Way. So this on the top right is the central part of our Milky Way, and in visible light we cannot see right into the center because there is a lot of dust particles between us and the center of the Milky Way. Because when I say a lot, I mean a lot in astrophysical terms. Actually, the space between us and the Milky Way is almost a vacuum. But whatever few dust particles are there, over that large time scale, they become a lot. And then they obscure the visible light from stars which is behind them. So we are not able to see into the center of our Milky Way. We see dark patches if we look at it in visible light. But in infrared light, we can see to the center of the Milky Way, just like in radio light. And because dust is transparent to both infrared and radio frequencies. And so this result I'm going to show you is a very fascinating result where a bunch of astrophysicists led by Andrea Ghez and collaborators, they imaged the very center of the Milky Way in infrared light. So I want to explain what I'm just going to show you. So here is the result, and I'm going to show you an animation and I'll explain why. So what you see here, these splotches, these are real data. They are false color pictures of a real image of the center of the Milky Way, and they are stars. They are stars in the very center of the Milky Way, this region. They're all labeled, as you can see. Now, this white star, it's a little confusing because it's star-shaped, but it's not a real star. It's just marking a position there. And this counter is giving a date. This is giving the scale in arc seconds, and this is giving the date. So what these people did was, starting 1995, they were imaging the center of the Milky Way in infrared frequencies at regular intervals. And then they put all these images together. So if these stars move, and you would expect that these stars, some of these stars at least, would move, you would see them at a different position at a different time. And so effectively, by putting all these images together in a sort of an animation, we can actually see how these stars move. And that is what I'm going to show you here. So this animation will loop. So to remind you again, the splotches are false color pictures of stars imaged in the infrared in the center of our galaxy. And the white star just marks a position. So what you can see very clearly is that all these stars are making, or most of them at least, are making clearly elliptical orbits around a point. That point is marked by the star. And it's the same point. All the stars are making elliptical orbits around the same point. This tells us very clearly that these are Keplerian orbits, which means we can establish a relationship between the mass of what is driving these stars into elliptical orbits and the distance of these stars from that point. And therefore, we can estimate the mass of that object at the position of the star, which is driving all of these things. And clearly that is not shining. We're not seeing any infrared light from it. We're not seeing any visible light either anyway, because we can't image this part, but we're not seeing any light from that position where this mass must be. But using the orbits, there are elliptical curves drawn to guide one's eye. Using the orbits, we can determine what is the mass of the dark thing which is driving all these things. We can do another thing. If you notice the object, this object with the yellow track, it is going very, very close to this position of the white star. And you can see that it goes very close to it and then emerges. So it's not disrupted, nothing has happened to it, which means that it has not collided with this dark thing, which is at the position of the star. Which means that this dark thing has to be smaller than the closest distance the star makes with that position, right? So that gives us an upper limit on the size. So putting all of these together, it turns out that the Keplerian orbits imply that the mass of the thing that is driving all these elliptical orbits has to be 4 million times the mass of our sun. And we know the size, as I said, because it has to be smaller than this distance. And that size and that mass put together clearly imply that it is a black hole that is at the center of our Milky Way. Now, black holes which are more than 1 million times the mass of our sun, they have a special name. They're called supermassive black holes. And it turns out that virtually every galaxy we've looked at in the cosmos has such a supermassive black hole in their very center. So there are stellar mass black holes scattered all over the galaxy, which are the result of stars dying. But there is a supermassive black hole of 1 million solar masses or more at the centers of virtually every galaxy we've looked at. Now, This is Gargantua. People who've seen Interstellar will know what this is. And what is this showing? So incidentally, Gargantua is a supermassive black hole. Its mass was more than 1 million times the mass of our sun. And this is showing what happens if some gas or stars or something comes in the close vicinity of a black hole. So what will happen is that such matter will spiral around the black hole because it is attracted by the gravitational force, and eventually it will get sucked in and plunge into the supermassive black hole, or any black hole actually for that matter. Even a stellar mass black hole, if gas and dust comes very close to it, then it will spiral around it and eventually plunge into the black hole. And that is what this the Gargantua was doing as well in the movie Interstellar. And the interesting thing is, if this happens, remember that in the Milky Way, the central black hole was dark. It was not emitting much light, so we couldn't see it. But if this happens, if a sufficient amount of matter comes swirling around the black hole and plunges into it, in the process of swirling around, it is accelerated to extremely high speeds, and therefore it is also heated to very, very high temperatures. As a result, this gas shines. So it shines in X-rays, it shines at a bunch of frequencies, and so we can then see it. So even though we may not have telescopes with sharp enough imaging to image stuff like this, we will see this very, very bright source of X-ray light, for example, which will be a telltale signature of a black hole. So we call such black holes accreting. Accreting means you're accumulating, the black hole is accumulating material, and that's swirling around and eventually plunging into it. So if a black hole is doing that, then we have a chance to actually see it because all that material shines. In fact, even though I said that stars leave black holes at the end of their lives and we're able to detect them if they are in binary systems by using the Keplerian idea and so on, and that there are about 10 million of them scattered all over the Milky Way, and we've actually measured masses of 65 or so, 66. The earliest black holes that came into our knowledge were the supermassive black holes, actually. They're very, very far away. The one in the Milky Way is the closest to us, but all the other galaxies are, of course, much further away than the Milky Way. But these black holes came into our horizon because of this process of accretion and this accreting material shining. In fact, it was rather confusing because in the very beginning, they used to look like stars, like this image, for example. So if you see this image, this thing is clearly a galaxy. You can see the spiral structure, but both these things look like stars. And it is only when you actually take the spectrum that it becomes clear that this one is a star. This is a spectrum of it, and it is showing you the typical black body spectrum and the absorption lines. But this one is showing very strong emission lines, which is not what a typical star does. So it actually foxed quite a few people, and this is Martin Schmidt, who was the person who stared at this spectrum where none of the lines could be recognized compared to laboratory values, because these lines had been shifted to a very large extent. And that is why they couldn't recognize the patterns. Remember, I said that Doppler shifting shifts the frequencies of laboratory determined spectra of atomic lines. But it was Martin Schmidt's insight and realization that this was just a very large shift that led to the discovery that some of these star-like objects are actually giant black holes which are accreting, and they are in the centers of galaxies. And we can't see the galaxies simply because we're blinded by the light from this accretion. And then the next step was to sharpen the images we could get with telescopes, and Ruby Payne Scott played a major role in this to get sharp images at radio frequencies using the technique of so-called interferometry, which I won't go into here in detail except to mention it, but this has now become a very common technique. As a result, especially at radio frequencies, when we image some of these galaxies, it turns out that the accreting supermassive black hole not only shines because of the stuff that is swirling around it, some of this stuff gets heavily magnetized and then gets funneled in two jets of plasma, bipolar symmetric jets of plasma, which are squirted out well outside the horizons of the galaxy itself into intergalactic space. And that is what these pictures are showing us. So these are false color pictures, and here the pinkish stuff is an image at radio frequencies, and the that is overlaid on an image at visible frequencies, where you can see the galaxy with all its stars, and then you can see other background galaxies and stars and so on. And overlaid on this is this radio picture, which is showing us the jets of plasma which is skirted out from the central accreting black hole. And this is another example of something similar. So how do we know that stuff is coming out? It could well be going in. Well, we know that because of this kind of a result, which is again very common and has been done for many, many galaxies. And what it is showing us is a very, very sharp zoomed in version of this image taken at different times and then put all together to give us an animation. And you can see that the things that are emitting the radio light are coming from different places in the sky as we go along in time. And if you look carefully, you can see that stuff is actually coming out from the central part. So we know for sure that this is outflow of plasma and not inflow from some, due to some unknown reason. So we know that it is directly related to the accreting supermassive black hole, which is at the centers of these galaxies. This is a simulation of, okay, I need to play this simulation separately because it's for some reason not playing in my but this shows, this is a computer simulation with the best physics, which includes general relativistic effects and magnetohydrodynamics, and it gives us an idea how matter which is accreting onto this supermassive black hole can create magnetic fields and then launch the plasma right out of that system into extragalactic space. So the green lines represent the magnetic field lines, which are twisted around because of the accretion, and the blue stuff represent plasma, which is squirted out into intergalactic space. So this is a computer simulation. This is not real data, but it gives us an idea that using the physics we know, one could possibly create these fantastic phenomena. Was that visible, Pitashta? The animation?
Yes, it's running. Yeah.
Okay. Okay. So now putting all of this together, remember we said that in the center of the Milky Way, there is a giant black hole. And indeed, in every galaxy like this that we've looked at, there are giant black holes in their centers. And when stuff comes very close to the black hole, it is sucked in, it starts to swirl around, it shines, and then finally plunges into the black hole. But some of it, due to the magnetic fields created, is squirted out in the form of these bipolar jets. And these are examples of that. Now, naturally, you can imagine that these jets will also affect the environment around them. And that is what this image shows us. So this is a superposition of two false color images, well, three false color images. There is the visible light image, which shows all these background stars and the galaxy in the center. The reddish image shows the image at radio frequencies, which shows this jets of plasma which are squirted out. And then on top of that is superposed the X-ray image, which is the bluish looking image. And you can see that there are cavity-like things in the X-ray image which coincide with these radio jets. So the X-ray light, we know, comes from the hot gas, the very, very hot gas which surrounds this supermassive black hole and galaxy and so on. And the jets seem to puncture holes in this hot gas, so that right where the jets are, there are these massive cavities. So just keeping that idea in mind, a very intriguing relationship came to light in the late 90s, which is a relationship between the mass of the black hole and the mass of the big galaxy that it hosts. Now remember that the black hole is in the very center of the galaxy, and it's a very small scale. So it cannot be that the galaxy, the mass of the galaxy and the mass of the black hole are related due to gravitational coupling. So this is just a pictorial representation of the relationship I'm talking about, and this is Laura Ferrarese, who played a major role in this discovery, and this is how the actual data looks like. So how is this explained? One way to explain it would be to say that, you know, galaxies come together and they merge because of gravitational attraction. And if each of them has a giant black hole, those giant black holes will also merge. And so you'll get a bigger black hole and a bigger galaxy. And this is partially true because we see a lot of evidence for galaxies which are coming together, and the simulations tell us that their black holes will also come together. There are many examples of this. This is one example where the imaging has been done not just of the galaxies and the stars in the galaxy, but also the X-ray gas. And the red stuff is hot gas, which is emitting X-rays, and these two blue things are also emitting X-rays, but much harder, that is much higher energy X-rays. And you can see that there are two very sharp sources of these X-rays, which represent accretion of matter around two supermassive black holes. So these two galaxies have come together and have disturbed, have resulted in a very big mess here, where all the stellar orbits are disturbed and so on. And in addition, the hot gas is disturbed as well, and the two central black holes are coming together. This is another example from my own work where you have this galaxy which is part of a triple, and it is actually the result of two merged galaxies. And we see, this is an infrared picture where we see the two accreting black holes here and here. This is actually a foreground star. It's not related to the galaxy, but this is an accreting black hole, and so is this. And we see it in both the emission lines from the hot gas here and here. We see it at radio frequencies with by imaging with a radio telescope. So these two sources correspond to these two, and they are both the accreting supermass pair of supermassive black holes. And we also see the same thing in an X-ray image, where the two accreting supermassive black holes are emitting X-rays. And so you might think that is what results in this relationship between the mass of the black hole and the mass of the galaxy, but it is more, it turns out that is not the whole story. And part of that story is that the accreting central black hole, when it spews out this material, that material interacts with the gas around, and that gas is what is forming stars of the galaxy. So there is this coupling, not just because two galaxies come together and merge, and so their black holes merge and make a bigger black hole, but also in a single galaxy, if matter comes near the supermassive black hole, then you get these jets of plasma which will then interact with the hot gas around it, and it will regulate the formation of stars. So all that said, it's still only circumstantial evidence for the existence of a black hole, because it is true that when you get these massive jets which go out into intergalactic space, the only way to make them is to have a giant black hole and stuff accreting around it. We know no other way to make these giant jets of plasma which come out of the galaxy into intergalactic space. But that's still only circumstantial evidence. So then how to really find a black hole? So this is the rationale for that. So suppose you have, suppose you had an ordinary dark object, very massive, and stuff started spiraling around it. It would light up and shine, and you would see something like this. These are not real data, these are just simulations. On the other hand, what happens if it is a black hole? And the movie Interstellar showed us what happens in Gargantua. What happens is that not only will you see this material shining, see in this picture, the material which is behind the black hole, we are not able to see because this thing is in the way. This is not a black hole. Let's say it's a dark object. And there's material behind it, which is also swirling into it, but we're not able to see it because this dark object is in the way. But what happens if the dark object is a black hole? It is going to curve the space-time so much that the light from behind is going to curve and come in front, and it's going to be visible to us. Similarly, the light is going to curve around the so-called lower part of the black hole and become visible to us. So if this dark object is a black hole, we wouldn't see this, but we would see something like this with this hat-shaped structure and this ring and so forth. So if we could image something very sharply, and that something were a black hole, then we could see this. So that's the that's the way to find a black hole, to find its silhouette. We can't see the black hole, but we hope to see its silhouette. And this was a hope for a very long time, but recently that hope has been realized. So this is a piece of sky where there is a galaxy called Messier 87. And this is the galaxy Messier 87, and these are all the background objects and the stars and whatnot. And a very fine, very sharp picture in visible light of Messier 87 does show us some jets of plasma. Okay, and here is a picture, many false color pictures at different frequencies. So this is the same thing I showed earlier, the visible light picture, which shows all the millions of stars in that galaxy. But from the center, there is a jet of plasma, which is visible. And this is what it looks like at radio frequencies. This is at visible light frequencies, and this is at X-ray frequencies. And this is zooming out now. So this jet is the same jet, and that is in here. And there is so much plasma which has been squirted out over the billions of years of its life that you see these more diffuse plasma structures. And this is even more diffuse, which is from an even earlier time. And so it has had time to come out and then diffuse. Now, this object was imaged with the sharpest telescope we have to date, and that is called the Event Horizon Telescope. And this was a telescope, it's not a single telescope actually, it's an array of telescopes which uses the principle I mentioned before of interferometry, in which Ruby Payne-Scott played a major role many decades ago. And this is a very sophisticated version of it, which uses all these telescopes situated all across the planet, and all of them none of them operate as single individual telescopes, but they all operate as an array. It's effectively an array of interferometers where the light received from one of a pair and the other of a pair are correlated rather than added up. And so you get a very sharp image, and this is Katie Bauman, who headed the, who's actually a computer science, who was a computer science student, and she headed the computing part of this, because as you can imagine, to create an image from this array is a very computationally intensive process. And what they got is this image. And you can see that it very much matches what we expect from a simulation, namely a ring around a dark circle in the center. So I've kind of come to the end of my talk, and I hope I've given a flavor to you of how astrophysics research is done using the small story around black holes. Astrophysics, of course, is a very vast subject. It is a very, shall I say, illustrative example of the use of the scientific method. I wanted to read out the description of what the scientific method is, a very famous description by Jawaharlal Nehru, where he said, "It is the scientific approach, the adventurous and critical temper of science, the search for truth and new knowledge, the refusal to accept anything without testing and trial, the capacity to change previous conclusions in the face of new evidence," this is very important, "the reliance on observed fact and not on preconceived theory, and the discipline of the mind. All this is necessary not merely for the application of science, but for life itself and the solution of many problems." Now, as you saw in the story that even I described today in this short time, science is meant to be objective, but it is not really objective in practice. You saw the example of Cecilia Payne-Gaposchkin, where she came to a certain conclusion that the sun and the stars are mostly made of hydrogen and helium, but was not believed. And she had to actually say in her thesis that this might be a spurious result. We don't know why her result was not believed. Some people would argue that because it came from a woman, it was not believed. The good thing is, of course, that she's been vindicated later on. The not so good thing is that she was not nominated for the Nobel Prize. It was her supervisor who actually didn't believe her who was nominated. These kind of things happen all the time. Even when it came to Einstein, remember I said that Einstein discovered the general theory of relativity, and in the same year, Carl Schwarzschild found a solution which told us about black holes. But Einstein didn't like black holes, even though it was a consequence of its own theory. A lot of people didn't like black holes. I remember that even when I was a PhD student, which was about 35 years ago, there were a lot of astrophysicists who didn't like black holes, and so they were trying to explain all these very energetic phenomena that we saw in the centers of galaxies as a consequence of just stars, of energetic processes within stars. Of course, the fact was that these jets of plasma, which were squirted out of the galaxy, out into intergalactic space, they were known at that time. And there was no way they could be explained by stellar processes, but there were still people who were very wedded to stellar processes and so didn't believe that there were black holes in there. That has changed, of course, and now everybody believes that these are due to black holes. But the point is, science is meant to be objective, but it is not objective in practice. Another example, a very striking example, which I didn't talk about, but it was very striking when I was a PhD student, actually, was this result, which was affectionately known as B2FH or B squared FH. Burbage, Fowler, and Hoyle were the authors of this paper, where they showed that the heavier nuclear elements were synthesized in stars as a result of nuclear fusion. And this was a very, very important paper. It combined the experimental results that Fowler had and the theory that Fred Hoyle had photosynthesis and the actual data from stars that Margaret Burbidge and her collaborator Jeff Burbidge, who happened to be her spouse, had. Now, Margaret Burbidge changed her name after her marriage, of course, and so the paper was Burbidge, Fowler, and Hoyle. But it was amazing to me that most people I encountered thought that the first author, Burbidge, was Jeff Burbidge and not Margaret Burbidge, even though they had read the paper. So there are all these very strange things which have really no place in science. So some people will argue that science itself is objective, the scientific method is objective, and it's only the scientific practice which is not objective. Others would argue that since scientific practice is a collective enterprise by all of us, social processes necessarily will be at work, and therefore science practice can never be objective. So what does one do about this? So I just wanted to leave you with a quote from Laura Ferrarese, whose result I described in my talk. And she says, the sense of achievement derived from concluding a scientific investigation, from obtaining data to publishing a paper, pales in comparison to the reward of improving the environment in which others can thrive. So I think that's a very telling quote, and I'll leave you with that. Thank you.
Thank you, Professor Shastri, for this very engaging lecture and the spectacular images and videos. We have a little time for a few questions. Shall we take some?
Yeah.
Yeah. So some questions have been typed in the chat box. I'll just read them out to you. One question is from Vijaya Raghavan, who asked that photons from back of the object will get observed by the object itself, right? That is the question.
Sorry, can you repeat that?
The photons from the back of the object will get observed by the object itself, right?
Yes, that is true. Yes. I mean, it depends on what we call the optical thickness. So it depends on the situation, the circumstances within the object that is emitting. So for example, the sun, the star, we only see the photons from the surface because the other photons are they don't come out. They sort of get absorbed within. So we see the photons from the surface. But on the other hand, all those jets that I showed you, where you had these jets of plasma being squirted out, there we see the whole jet. That is, we see the photons from the front as well as from the back. It's like a gas flame. You know, if you look at the flame of a gas, it's like we see photons from all parts of the flame. We don't see photons only from the front part. So that kind of thing we call optically thin or transparent is one way to think about it. And yeah, so if you're sitting inside that, you will of course see photons from all around you.
The next question is by Utpal, who asks, won't the rotation of the object obscure the delay reading?
I don't know which delay they're talking about. Do you want to unmute them and have them ask the question? Hello?
I'll just unmute this person.
Yeah. Yeah.
Yeah, Miss. Mr. Utpal, can you unmute yourself? I'm trying. It's not happening. Mr. Utpal, can you unmute yourself? Mr. Utpal, I think you're unmuted. You can ask your question. Okay, I don't hear anything from him.
So then, can you just repeat the question? I'll try to answer it as is.
1 second. Won't the rotation of the object obscure the delay reading?
Okay, maybe they mean that if they're talking about the light travel time argument, maybe, and so this delay between the photons in front and the photons at the back. What we are seeing is a very sort of averaged kind of thing, and so yeah, in principle, the rotation would complicate what we are seeing, but I was talking about a hypothetical non-rotating case.
The next question is by the same person, Utpal. How are Gargantuan type black holes formed on comparison with stellar ones?
Yeah, that's a very interesting question. It's something that I wanted to go over, but then I limited in order to save time. So it is a question as to how these giant black holes form. Is it that you have stellar mass black holes form because stars die, and then these stellar mass black holes come together and merge and make bigger and bigger black holes and then make the giant black holes? And it seems that that is not the case, because we've seen very, very big black holes with masses of 1 billion or more in the very, very far reaches of the universe. So very early on in the life of the universe. So there is not that much time since star formation started and the stars dying and then them merging and then building up from being a few solar masses to 1 billion solar masses. There was simply not enough time. So one idea, which is one of the champions, is Priyamvada Natarajan, and there are many others, for direct collapse of gas into very, very massive black hole seeds, as we call them. So this is where you wouldn't have, so it's not the result of stellar death, but matter, even before forming stars, it would a large amount of matter would collapse into a black hole, which is several thousand solar masses. And then it would go through the process of accretion. So you see, both accretion and mergers, both of these increase the mass of the black hole. So this kind of a seed would increase its mass both by mergers and by accretion, and then maybe reach the masses we see in the centers of galaxies.
The next question by Boma Kanti. Thank you for a wonderful talk and the motivation as well. My question is regarding the minimal surfaces in black holes. Is this only a mathematical construct, or can we actually image this?
Okay, so the silhouette that we talked about, that is the so-called event horizon of the black hole. And that was what was predicted by general theory and the simulations also, that if you have stuff swirling around a black hole, it'll all get heated and shine, and you will see the silhouette of the event horizon. And the result from the Event Horizon Telescope exactly matches this prediction. So that dark, dark image, that is, can you see my screen?
Yes, I can see. You can see.
Circular image is the silhouette, and it exactly matches the predictions because, as I said, this is a galaxy which was very well studied earlier. So there are estimates of what its black hole mass should be from independent measurements as well, and it all fits in. It all hangs together. And so the silhouette is the silhouette of the event horizon. Does that answer the question? For some reason, the Teams window has disappeared, so I'm not able to see the question answer box. But if you can ask them if that answered the question, that'd be good.
Yeah, they got the answer, it seems. They
Okay.
replied, yeah. There's somebody called Rajeshri who has raised a hand. I cannot unmute you. Can you unmute yourself and ask?
Yeah, I have unmuted myself.
Yeah,
Can you
yeah,
hear?
please ask it.
Yeah.
Yes, yes.
Yeah. So, ma'am, very nice talk. I had one question. Since I'm not from this field, I don't know much about it. My question is that so in the center of a black hole, it's a singularity, right?
Yes.
Yes. So if light even cannot escape a black hole and it enters the black hole, then the information the light is carrying, is it lost or it's stored in the black hole? Like, I mean, it's there, but we cannot access it. Or is it completely shredded? I mean, the information the light is carrying with itself.
Yeah, so I should say, like you, that is not my area of expertise. So, you know, I only investigate what happens outside the black hole. And that's the only thing we have evidence for. Things that happen inside the black hole at the moment, they are in the regime of speculation. I would recommend, so in the University of Colorado Boulder, they have a site where they have lots of interesting stuff about what happens inside a black hole. And I would recommend that you go there. But I cannot myself answer that question.
Thank you, ma'am.
There's another question by Muni Kumar. Thanks a lot for the nice lecture, madam. Can we expect an other element exist in interstellar from where we will get X-ray images?
No, interstellar. So when I said interstellar, I meant the movie. I hope that was understood. You know, Interstellar was a science fiction film, and it involved, the story involved a black hole, and they had named it Gargantua and so on. The special thing about it was that a very renowned astrophysicist was also an executive producer of the film, and so the simulations that we saw in the film, he was involved in that, and it was they were correct simulations, you know, with correct as in they use the best physics that we know. He got the physicist is Kip Thorne, and he got the Nobel Prize later. And those simulations were actually published as a journal paper, a research paper as well. So that was the simulation, and so that's what I meant. So yes, I mean, in the movie there is no X-ray telescope. But if one, our X-ray, the real X-ray telescopes we have, we do look at such giant black holes, and they do emit radiation in the way it is expected. But Gargantua itself is a fictitious black hole in the film.
The next question is, what is emitted by the AGN? Is it ionized gas?
Ionized gas surrounds the AGN. So to explain to the other leaders, the others in the audience, AGN stands for active galactic nuclei or nucleus, and a giant black hole in the center of the galaxy, which is accreting matter and shining, that is technically referred to as an active galactic nucleus. What happens is you have, so the idea is that you have the black hole, you have the accretion disk around it, and then there is the environment of the galaxy as a whole. That is, there are all the stars, and in between the stars there is this interstellar gas. And so the interstellar gas around, in the close vicinity of the accreting black hole will get ionized. and we will see emission lines from it. The gas which is much further away, because the light from the accretion around the black hole, will start to dim as you get further and further away, and that gas will not be ionized by the accretion around the black hole. Instead, that gas will tend to get ionized by the stars if it is near some stars. So I hope I answered that question.
The next question, I think that will be the last question by somebody called Manya.
Ma'am, I had one question.
Okay, let me read the next question. What is meant by diffused plasma?
Well, plasma is ionized matter, and diffuse is just that, it kind of spreads. So there is this ionized, so plasma is just the ionized state of matter, which we see on Earth as well, right? A gas flame, that's plasma. But what happens in the black hole context is that when you have this accretion happening, and that accretion material is accelerated and heated to very, very high temperatures, 10 million and higher, there are magnetic fields which are created because of the ionization and the systematic movement and so on. There are magnetic fields that are created, and so some of the plasma does not plunge into the black hole, but is instead squirted around these the magnetic fields and out into intergalactic space.
I think we'll take the very last question.
Ma'am, I had one question.
Yeah, that I'm reading your question.
No, ma'am. For some reason I can't access the chat, so that's why I couldn't ask.
I can't see your name. Can you raise your hand?
No, I don't have that option either over here.
Okay, go on.
Okay, let them just ask.
Yeah.
Yeah. So thank you, ma'am, at the outset for such a wonderful lecture. My question is that when we have these jets of plasma coming out, is it possible that they can cause compression in the ISM so far as to create new stars?
Yeah. Yes, that is certainly a possibility, and there is evidence sometimes that actually happens. So it could be either way. It could be that they heat the gas around them, so then the gas cannot form stars, because in order to form stars you need cold gas. It could also be that they compress the gas, as you're saying, and then the stars form, maybe not at exactly the edge, but it leads to a compression of the cold gas, and then that forms stars. So that is called, it is called jet-induced star formation intuitively, and there is some evidence that happens.
Thank you, ma'am. Thank you, ma'am.
The last question by Dr. B.G. Shivaprasad. What happens to the huge mass which enters the black hole? Will it get converted into energy and emit light?
Not as far as we know. The mass that enters the black hole, it just enters the black hole, and the black hole has a higher mass now than it had before. So it becomes therefore it also becomes a larger black hole, because remember the relationship between R and M, right? So if you have more mass, you'll get a larger black hole. So will it get converted into energy inside the black hole? I don't know. As I said, I only look at things that happen outside, and we don't know what happens inside the black hole. We have no evidence for it, but there is a lot of theoretical work on that and speculation, and so you should consult the experts in that. Will it emit light? So the simple answer is no, but there has been a theory by Stephen Hawking which combined quantum physics and gravity and so on, and the prediction is that there will be some radiation that is emitted by the black hole. It's called Hawking radiation. But now the thing is that this radiation is roughly inversely it goes inversely as the mass of the black hole. In other words, if you had very, very small black holes, they would sort of emit a lot of Hawking radiation and evaporate and vanish in a very short time. But the bigger the black hole, which means the more massive it is, the lower the amount of Hawking radiation. So it would take a very long time for that black hole to evaporate. It would also, it's not clear that that kind of Hawking radiation would be actually detectable. And so far, it has not been detected. And the black holes that we are looking at, stellar, few solar masses to, 1 billion solar masses, the Hawking radiation predicted from those is very, 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 very low. So that has not been seen. There is somebody.
Yeah.
So, if the black hole is evaporating by emitting Hawking radiation, then if accumulative Hawking radiation should account for the mass of the black hole. Is it true?
Sorry, the Hawking radiation, I didn't get your last sentence.
If we accumulate all the Hawking radiation, if we could accumulate all the radiations that have been coming out of the black hole, then it should be proportional or equivalent to the mass of the black hole. Is it true?
When it finally evaporates, I guess.
Yeah. When it finally evaporates.
Yes. I've not thought about this. My guess is yes, but I would need to check. In fact, you should check it yourself.
Okay.
But my guess is that is true.
Yes, someone is making a request to take her question. Shall we?
Yeah. Go ahead.
Why do we observe jets on two sides of black hole instead of as coming from sphere?
Yeah. So if you remember, the reason we think is this accretion, right? So the accretion is happening around the black hole, which is in a plane, which means that the symmetry is broken. So the accretion is not happening, in a kind of a spherical fashion. It's happening along a plane. And so then the symmetry is broken into an axisymmetry. So it's an axisymmetric system. So then it's not surprising, right, that when the magnetic fields which are created and which is cutting out come out in two directions, rather than everything spherically, in a spherically symmetric way. Does that answer the question?
I think so. Yeah, she says yes, ma'am. Thank you. So, shall we call it a day?
Yes. Sure.
Yeah.
I mean, if you've dealt with all the questions,
Yeah, I think I have read out all the questions. There was a request for the slides. We have recorded a lecture and we'll be putting it up on IISc website, so they can access it from there. Thank you, Professor Shastri, for this engaging lecture and giving us a chance to know about the universe. Thank you so much, and we hope to have you again in some other, lecture series that we will hold. Thank you so much.
Sure. Thank you. Thank you very much. It was fun.